You wake up. Your body holds together. The chair supports you. The floor beneath you stays solid. The atoms in your bones, your skin, your blood, they do not implode into nothingness. Why not? What invisible hands keep every particle from crushing itself into oblivion? We know gravity wants to collapse everything. We know electromagnetic forces try to tear nuclei apart. But something stronger resists. Something absolute. Rules written into the fabric of reality that say no further, no smaller, no more. Welcome to the only thing standing between us and nothingness. December 14, 2024, both peer-reviewed sources tracking the latest experimental confirmations of quantum field theory predictions that keep matter stable. Now back to the information. By 1927, he publishes what becomes known as the Heisenberg Uncertainty Principle. The equation is simple. Delta x times delta p must be greater than or equal to h divided by 4pi. Position times momentum cannot both be zero. You cannot know both exactly, ever. The more you pin down where a particle is, the less you know about how fast it is moving. This is not a measurement problem. This is reality. Why does this matter for collapse? Because if you could compress a particle to an exact point, its momentum would explode to infinity. The particle would have infinite energy. It would tear apart. Instead, Heisenberg's limit says no. When you squeeze an electron into a smaller space, its momentum uncertainty increases. It starts moving faster, not because you heated it, because the universe demands it. The tighter you pack the electron, the more violently it resists. This creates pressure, real measurable pressure that pushes outward. This is not thermal, this is quantum, and it is the first wall against collapse. That gives you 1.054 times 10 to the negative 34. This number is tiny, but when you compress matter to nuclear densities, when you pack electrons into volumes smaller than an atom, this number becomes the only thing standing between you and infinite compression. Every solid object you touch owes its resistance to this principle. Press your hand against a wall. The wall does not give because electrons and its atoms cannot be compressed beyond Heisenberg's limit. Their position uncertainty is already minimized. Their momentum uncertainty is maximized. They push back with quantum fury. The scattering pattern matches Heisenberg's predictions to within 1%. Published in Physical Review Letters, July 1973. The uncertainty principle is not theory. It is measured fact. For that, you need a second rule, one discovered in 1925 by Wolfgang Pauli. The universe says no with absolute force because they have no choice. Pauli's rule forces them upward. This creates pressure, enormous pressure, pressure that does not depend on temperature. A white dwarf can cool to near absolute zero, and the degeneracy pressure remains cold as death but unyielding as steel. For comparison, atmospheric pressure on Earth is 100,000 newtons per square meter. White dwarf pressure is 200 billion times greater. This pressure supports the entire mass of a star, one solar mass compressed into a sphere the size of Earth, against gravity that would otherwise crush it into a black hole. He calculated that electron degeneracy pressure could support a white dwarf indefinitely, even after nuclear fusion stopped, even after the star cooled completely. His paper in Monthly Notices of the Royal Astronomical Society, December 1926, page 607, showed that white dwarfs are quantum objects, stars the size of planets held up by rules that apply to particles smaller than atoms. The connection between the very small and the very large, proven in math and confirmed in observation. Not even quantum particles forced into higher states by Pauli's rule. When electrons hit relativistic speeds, the pressure stops increasing as fast. Gravity catches up. At one point, four solar masses, the limit is reached. The Chandrasekhar limit, calculated in 1930 by Subramanian Chandrasekhar aboard a ship from India to England, age 19. Published in Astrophysical Journal, July 1931. At this mass, electron degeneracy pressure fails. The white dwarf collapses. Electrons merge with protons. Neutrons form. The core implodes in less than a second. When a white dwarf exceeds the Chandrasekhar limit, or when a massive star's core collapses in a supernova, the result is a neutron star, a sphere 10 kilometers across. 1 to 2 solar masses compressed into the size of a city. Density of 4 times 10 to the 17th kilograms per cubic meter. A teaspoon weighs 5.5 times 10 to the 12 kilograms. 900 times the mass of the Great Pyramid of Giza, in 1 teaspoon. Neutrons are fermions. Pauli's rule applies. They cannot occupy the same state. As the core collapses, neutrons pack closer. They fill lower energy states. When those fill, they climb higher. They move faster. Neutron degeneracy pressure builds. At nuclear densities, this pressure is far stronger than electron degeneracy. It halts the collapse. The star rebounds. The shock wave blows off the outer layers in a supernova explosion visible across the galaxy. The core remains. A neutron star, dead, cold, but stable. The limit is approximately 2 to 3 solar masses. Above this, even neutron degeneracy fails. Neutrons cannot move faster than light. Gravity wins. The star collapses into a black hole. The pulsar PSRJ 0348 plus 0432, observed in 2013, has a mass of 2.01 solar masses, the most massive confirmed neutron star at the time, published in Science, October 25, 2013. These masses fall within the predicted range. No neutron star has been observed above 3 solar masses. The limit holds. Neutron degeneracy pressure prevents collapse up to a point. Beyond that point, nothing in the universe can resist gravity, not quantum mechanics, not Pauli, not any force we know. The force that holds atomic nuclei together despite electromagnetic repulsion between positively charged protons. This force is the strongest in nature. At a distance of 0.8 femtometers, 8 times 10 to the negative 16 meters, smaller than the radius of a proton, the strong force is 100 times stronger than electromagnetism, 1 million times stronger than the weak force, and 10 to the 38 times stronger than gravity. Gravity is a whisper, the strong force is a scream. For 2 protons in a helium nucleus, separated by 2.5 femtometers, the repulsive force is about 40 newtons. This force could support a mass exceeding 20 kilograms against Earth's gravity. For particles this small, this is enormous. It binds nucleons together into nuclei. It creates binding energy. When protons and neutrons combine to form a nucleus, the total mass decreases. The missing mass converts to energy according to Einstein's equation, E equals mc squared, published 1905 in Annalen der Physik. This binding energy is what holds the nucleus together. For helium-4, the binding energy per nucleon is 7.07 million electron volts. For iron-56, the most stable nucleus, it is 8.8 million electron volts per nucleon. Compared to 13.6 electron volts to ionize hydrogen's electron, nuclear binding is 500,000 times stronger. As long as nucleons stay close, within 2 femtometers, the strong force dominates. Beyond that distance, it drops off exponentially. This short range is why heavier nuclei need more neutrons. Neutrons add strong force attraction without adding electromagnetic repulsion. In uranium, with 92 protons, there are 146 neutrons. The neutrons space out the protons, keeping them within reach of enough neighbors to maintain binding while spreading out electromagnetic repulsion. Medicines were discovered in 1947. Yukawa received the Nobel Prize in 1949. The strong force was proven. Published in its modern form by Murray Gell-Mann, Harold Fritsch, and Heinrich Leutwiler in 1973, building on earlier work by Gell-Mann and George Zweig in 1964, who proposed quarks. QCD describes how quarks interact via the exchange of gluons, particles that carry color charge, not actual color, a quantum property. Quarks come in 3 colors, red, green, blue. Gluons carry combinations of color and anticolor. There are 8 types of gluons, each carrying a different color charge mixture. Red and anti-red, green and anti-green, also color neutral. You cannot pull a single quark out of a proton. Try it. Apply energy. The gluon field between the quarks forms a flux tube. The more you pull, the more energy goes into the tube. At some point, the energy in the tube becomes sufficient to create a new quark-antiquark pair. The tube snaps. You now have 2 mesons, both color neutral. But you still do not have a free quark. This was confirmed at Petra, a particle accelerator in Hamburg in 1979. Physicists observed 3 jet events, fire an electron and positron together at high energy. They annihilate, quarks and antiquarks form. But instead of seeing isolated quarks, detectors recorded jets of particles, mesons and baryons, spraying out in 3 directions. The quarks immediately combined into colorless hadrons. Published in Physics Letters B, December 1979. Color confinement is real. Quarks are permanently imprisoned inside hadrons. At the temperatures and pressures found in neutron star cores, 1 to 2 times 10 to the 32 pascals, temperatures up to 1 trillion Kelvin in the first second after formation, quarks remain bound. The neutron star does not dissolve into a quark soup, at least not under these conditions. Theoretical models suggest that at even higher densities, above 5 times 10 to the 18th kilograms per cubic meter, quark matter might form. Quarks might move freely in a quark gluon plasma. But even then, they remain confined within the star. No quark escapes into space. Color confinement holds. Required to separate 2 quarks increases linearly with distance. The string tension is approximately 0.2 giga electron volts per femtometer. Pull 2 quarks 1 femtometer apart, and the binding energy increases by 200 million electron volts. Pull them 2 femtometers apart, and it increases to 400 million electron volts. This linear growth means no finite energy can separate them. Confinement is absolute. Proving this mathematically is one of the 7 Millennium Prize problems announced by the Clay Mathematics Institute in 2000. Solve the problem, provide a rigorous proof of color confinement in non-abelian gauge theory, and win $1 million. As of December 2024, no one has claimed the prize, but experimental evidence is overwhelming. Decades of particle physics experiments, hundreds of measurements, millions of collision events, not a single free quark observed, ever. Protons repel protons, but electrons surround nuclei. The atom is electrically neutral overall. Why does a solid resist compression? You press your hand on a table. The table pushes back, not because of Pauli exclusion alone, because of electromagnetic repulsion between electron clouds. As atoms approach each other, their electron clouds overlap. Electrons repel. The closer they get, the stronger the repulsion. This is the force you feel when you touch something. This is what makes matter solid. You get 10 to the 16 newtons for a mole of electron pairs. Electromagnetic forces in bulk matter are immense. This is why you cannot push your hand through a table. Trillions of electrons push back. The force followed an inverse square law to within experimental precision. Published in Mémoires de l'Académie Royale des Sciences, 1785, page 570. Later experiments refined the measurement. By 1970, tests confirmed Coulomb's law to 1 part in 10 to the 16th. Published in Physical Review Letters, August 1970. It shapes chemistry, it determines bond lengths, it sets the size of atoms. Without it, electrons would orbit infinitely close to the nucleus. With it, electrons settle at distances where electromagnetic attraction to the nucleus balances kinetic energy and repulsion from other electrons. For hydrogen, this distance is 0.529 angstroms, the Bohr radius, calculated in 1913 by Niels Bohr. Published in Philosophical Magazine, July 1913. This distance is not arbitrary. It emerges from balancing forces. Electromagnetic repulsion plays a role, especially in multi-electron atoms, where electron-electron repulsion pushes electrons into higher orbitals. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Wikipedia's physics articles, updated December 16, 2025, and the University of California's Physics LibreTexts project, updated March 16, 2025, both comprehensive databases of experimental results and theoretical frameworks in quantum mechanics. Now back to the information. But electromagnetic forces alone do not prevent total collapse. Not under extreme gravity, not in white dwarfs, not in neutron stars. For that, you need quantum degeneracy. For that, you need the exclusion principle. Electromagnetic repulsion contributes to the pressure in ordinary matter, solids, liquids, gases, but at stellar densities, degeneracy pressure dominates. Electromagnetism sets the scale of atoms. Degeneracy sets the limit of compression. Together, they form a multi-layered defense. Push against ordinary matter, and electromagnetic repulsion resists. Compress matter to extreme densities, and quantum degeneracy takes over. Compress further, and neutron degeneracy holds. Compress beyond that, and the strong force resists at nuclear scales. Go even smaller, and color confinement says no more. Electromagnetic forces at angstrom distances. Degeneracy pressure at densities of 10 to the 9 kilograms per cubic meter and above. Neutron degeneracy at 10 to the 17 kilograms per cubic meter. The strong force at femtometer distances, color confinement at quark scales. They overlap, they reinforce. They create a hierarchy of resistance against collapse. They are exact within measurement limits. Planck's constant, 6.626066957 times 10 to the negative 34 joule seconds. Measured to 9 significant figures. Published by CODIDA, the Committee on Data for Science and Technology, in 2018. The Bohr radius, 0.52917 72109 times 10 to the negative 10 meters, measured to 12 significant figures. The electron mass, 9.109383715 times 10 to the negative 31 kilograms, measured to 12 significant figures. The proton mass, 1.6726 to 19237 times 10 to the negative 27 kilograms, same precision. The speed of light, 29,979,245 8 meters per second, defined exactly since 1983. These numbers are not guesses. They are measured, repeatedly, by hundreds of laboratories, using different methods, independent confirmations. When physicists at NIST, the National Institute of Standards and Technology, measure the electron charge, and physicists at PTB, Physikalische Technische Bundesanstalt in Germany, measure it, and physicists at NPL, the National Physical Laboratory in the UK, measure it, they get the same answer to 12 decimal places. This is not coincidence. This is reality revealing itself through measurement. These constants define the structure of matter. They set the strength of forces. They determine the scale of degeneracy pressure. They decide when matter collapses and when it holds. Structure constant as laboratory measurements today. The fine structure constant, alpha, equals approximately 1 divided by 137. It describes the strength of electromagnetic interactions. If alpha changed over time, spectral lines would shift. They do not. Published in Physical Review Letters, March 2013. Measurements constrain variations in alpha to less than 1 part in 10 to the 6th per billion years. Over the entire history of the universe, these constants have not changed. The rules that prevent collapse today are the same rules that prevented collapse when the first stars formed, when galaxies assembled, when atoms first existed 380,000 years after the Big Bang. Their masses cluster around 0.6 solar masses. They do not exceed 1.4 solar masses. The Chandrasekhar limit holds. We observe neutron stars in distant galaxies. Their masses range from 1.2 to 2.2 solar masses. None exceed 3 solar masses. The Tolman-Oppenheimer-Volkoff limit holds. We observe supernova explosions in other galaxies. The light curves match models based on electron capture and neutron degeneracy pressure. The physics is universal. Distance does not matter, time does not matter, the rules apply. Molecules would not form, your body would compress, not slowly, instantly. Gravitational potential energy, no longer balanced by degeneracy pressure, would convert to kinetic energy. Matter would heat, atoms would collide, fusion would occur. The Earth would become a star, then a white dwarf, then, as mass accumulated, a neutron star, then a black hole, all in seconds. Protons, no longer bound, would fly apart under electromagnetic repulsion. Every atom heavier than hydrogen would disintegrate. Carbon, nitrogen, oxygen, all gone. The elements would not exist. Stars would not shine. Fusion would not occur. The universe would be hydrogen and helium, slowly dispersing, never condensing, never forming planets, never forming life. Hadrons would dissolve. Matter as we know it would cease. No protons, no neutrons, no atoms. Only a quark-gluon plasma, a soup of fundamental particles that might or might not be stable. We do not know. We have never observed a universe without confinement. We cannot. Because confinement is absolute, at least in our universe, at our energy scales, at our temperatures. The rules exist. They do not fail. They have been tested billions of times in particle accelerators. Every collision at CERN, at Fermilab, at SLAC, at Keck in Japan, at DSY in Germany, every collision is a test. Fire protons at each other at energies of 13 trillion electron volts. Smash them together, watch the debris, count the particles, measure their properties, compare to theory. The predictions match, to within fractions of a percent. Sometimes to within parts per million. Quantum chromodynamics predicts 3-jet events. They occur. The theory predicts quark confinement. It holds. The theory predicts gluon self-interaction. It is observed. Millions of collision events analyzed. The results are consistent. The rules hold. Strong force at 10 to the negative 14 meters. Electromagnetic repulsion at 10 to the negative 10 meters. Degeneracy pressure at densities above 10 to the 9 kilograms per cubic meter. Neutron degeneracy at 10 to the 17 kilograms per cubic meter. Gravity, trying to compress everything, resisted at every step. Your nuclei do not explode because the strong force overwhelms electromagnetic repulsion. Your cells do not dissolve because molecular bonds, held by electromagnetic forces, keep atoms together. Your bones do not crumble because electron clouds repel each other under compression. You stand because the ground resists. The ground resists because atoms resist. Atoms resist because quantum mechanics says they must. This is the structure of reality. Remove one rule and the structure fails. Remove Pauli exclusion and matter collapses. Remove the strong force and nuclei disintegrate. Remove color confinement and protons dissolve. The universe is not arbitrary. It is governed by laws, laws that we have discovered, laws that we have tested, laws that we have measured to extraordinary precision. Heisenberg's inequality, delta x times delta p greater than or equal to h bar over 2. Pauli's rule, no two fermions in the same state. Coulomb's law, force proportional to charge product over distance squared. The strong force, binding energy, proportional to nucleon number. Color confinement, quarks always in color neutral combinations. 5 rules, each one absolute, each one necessary. Remove any one, and matter, as we know it, cannot exist. But here's the deeper point. These rules were not invented, they were discovered. Heisenberg did not create the uncertainty principle. He found it. Pauli did not design the exclusion principle. He observed it in atomic spectra and worked out the math. Coulomb did not dictate the inverse square law. He measured it. Yukawa did not ordain the strong force. He predicted it based on nuclear binding energies, and experimentalists confirmed it. Gell-Mann, Fritz, Leutwiler did not imagine color confinement. They deduced it from quark behavior in high-energy collisions. As the universe cooled, quarks combined into protons and neutrons. 380,000 years later, when the universe cooled enough for electrons to bind to nuclei, the exclusion principle governed electron configuration. Stars formed, cores compressed, degeneracy pressure resisted, white dwarfs formed, neutron stars formed, black holes formed. The sequence is fixed, the rules dictate the outcome. And we are here because the rules balance. If electron degeneracy were weaker, white dwarfs would collapse at lower masses. More supernovae would occur, more neutron stars would form. The galaxy would be flooded with high-energy radiation. Life would struggle. If the strong force were weaker, fusion in stars would be less efficient. Stars would burn faster. They would exhaust fuel before planets could form. If color confinement were weaker, protons might decay, matter would be unstable, atoms would not last long enough for chemistry. The rules are not just absolute, they are finely tuned, not by design, by accident, or by necessity. We do not know why the constants have the values they do. We only know that they do, and that if they were significantly different, we would not be here to measure them. The weak version. We observe a universe compatible with our existence because incompatible universes contain no observers. If Pauli's principle did not hold, matter would collapse. No stars, no planets, no life, no us. We exist in a universe where the rules allow complexity, allow stability, allow matter to resist collapse long enough for galaxies to form, for stars to cook heavy elements, for planets to cool, for chemistry to create life, for life to evolve intelligence, for intelligence to discover the very rules that allow its existence. Why does the Pauli principle hold? Why is color confinement absolute? That is the only thing that matters. You exist in a universe with rules. Rules that prevent collapse, rules that allow structure, rules that permit existence. Without them, there's only void. With them, there is matter. There is light, there is life, there is you. For a fraction of a second, the combined mass exceeds the Tolman-Oppenheimer-Volkoff limit. Neutron degeneracy pressure fails. The object collapses. A black hole forms. Gravitational waves ripple through space-time. Detectors at LIGO and Virgo record the signal, published in Astrophysical Journal Letters, October 2024. The mass limit is confirmed again. Neutron degeneracy holds up to 2.9 solar masses. Beyond that, nothing stops collapse, not even the strongest quantum mechanical pressure known. General relativity predicts a singularity at the center, a point of infinite density. Quantum mechanics says this cannot be. Something must stop it. But we do not know what. We do not have a theory of quantum gravity. We cannot calculate what happens inside a black hole. The rules break down, or they continue in ways we cannot yet describe. Beyond neutron degeneracy, beyond the Tolman-Oppenheimer-Volkoff limit, we enter the unknown. Black holes exist. We observe them, we measure their masses, we detect their gravitational waves, but we do not understand their interiors. We do not know if matter truly collapses to a point. We do not know if singularities are real, or if some quantum effect prevents infinite density. We do not know if the rules continue, or if new rules take over. But we know this. For every object below the black hole threshold, the rules prevent collapse. Planets resist because of electromagnetic repulsion and degeneracy pressure. White dwarfs resist because of electron degeneracy. Neutron stars resist because of neutron degeneracy and repulsive nuclear forces. These are not temporary defenses. They are permanent. A white dwarf can sit for trillions of years, cold and dark, supported entirely by quantum mechanical pressure that does not diminish. A neutron star can exist indefinitely, its neutrons packed at nuclear density, resisting gravity with zero thermal support. The rules do not tire. They do not weaken. They do not fail. The uncertainty principle, the exclusion principle, degeneracy pressure, the strong nuclear force, color confinement, electromagnetic repulsion, each rule a barrier, each force a defense, each principle absolute. Together, they form a hierarchy of resistance, from quarks to atoms to bulk matter to stars, from the smallest scales to the largest, from the earliest moments of the universe to the present day. The rules hold. The universe remains structured, matter remains stable, and we remain here to witness it. Neutron mass, 1.675 times 10 to the negative 27 kilograms. Speed of light, 299,79245 meters per second. Coulomb's constant, 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. Chandrasekhar limit, 1.44 solar masses, Tolman-Oppenheimer-Volkoff limit, 2.2 to 2.9 solar masses. Nuclear density, 3 times 10 to the 17 kilograms per cubic meter. Strong force range, 2.5 femtometers. QCD string tension, 0.2 giga-electron volts per femtometer. The evidence is overwhelming. The rules are real. They work. They hold. They have held for 13.8 billion years. They will hold for trillions more. The Pauli principle does not fade. The strong force does not weaken. The rules are embedded in the structure of space-time itself. They are not phenomena. They are laws. Fundamental, unchanging, absolute. Rules that create order from chaos. Rules that allow complexity. Rules that permit life. You do not collapse because the universe will not allow it. Principles that hold everywhere, always, without exception.